Good day to all. So, therefore, we are now in the third lecture on the packed bed adsorber design, right. So, if you remember, if you recall, in the last class we had discussed the packed bed adsorber. We had decided, or rather we had fixed on the contactor dimensions, the mass of adsorbent that we require, and also we had decided upon the cycle time, and we were about to start the evaluation of the pressure drop. So, today we start with the discussions on estimation of pressure drop, and after that we will be going into two illustration problems. Now, this pressure drop, as I had mentioned in the last class, it is something a very important parameter, because the processing rate, it can be limited by pressure drop. And if you recall, if you have a very high pressure drop, what happens? It can result in the lifting of the bed, or it can result in the bed compaction, depending upon the direction of the fluid flow. Again, suppose if you would go for very low pressure drop, then there are chances of uneven distribution and channeling. So, therefore, we find that to keep the power cost as low as possible, generally most of the adsorption plants, they operate with a very small pressure drop, and we would always like to go for larger particles in order to reduce the pressure drop, and we would also like to keep the velocity low, not only from pressure drop considerations, but to ensure that equilibrium is attained between the fluid and the adsorbent, and so therefore, maximum adsorption is possible under the particular operating conditions. So, usually there are certain guidelines. You must have found that during the entire course of the discussion on the design, I have given you several guidelines which you might consider, and also several checks. So, there are certain guidelines which are provided here for the gaseous and the liquid services using spherical, granular, or the extruded adsorbent particles with a particular, when the size lies within a particular range, and this particular size, it is defined in terms of the nominal particle size. And we find that typically when the vapor phase is flowing through a carbon bed, adsorption is going on, the pressure drop typically lies between 8 to 35 centimeters of water column per meter of bed, and more or less I have also listed down the pressure drop range as a function of the fluid velocity, under which we can have uneven distribution, both upflow and downflow are possible. Only downflow operation is possible, because when we go for upflow, this particular velocity, it is going to result in the lifting of the bed. It is important for you to remember that the velocity for lifting is less than the velocity for velocity which brings about bed compaction. Now, so therefore, what we do? We first find out the pressure drop, then we see whether it falls within the ranges which has been specified here. How do you go to find out pressure drop? This is basically flow through packed bed. You would recall that in your fluid flow classes, you have studied that for estimating the pressure drop through packed bed, what do? We use air gun equation. So, therefore, in this particular case also we use air gun equation. I have listed down the nomenclatures of each and every terms that have been used here, along with the relevant dimensions, because since it is a empirical equation, it is important that you use the same units that have been specified here, so that these constants, they are applicable. And naturally, for this particular case, the Reynolds number, it is defined as shown, and for non-spherical particles, the Reynolds number term through the dP effective, it contains a term on the particle shape factor as well. Now, when we go to use this air gun equation, there are certain things that we need to keep in mind when you are using. Definitely, we have to use it, but there are certain things which you need to keep in mind. First thing is the constants that are there. These constants, they are applicable for certain, they have been derived for certain specific packings. So, therefore, when we are using granular or pellet form of particles, This equation may not be very strictly valid for adsorption columns. The other important thing is this particular equation, it is applicable for steady state conditions. So, therefore, when the velocity is changing rapidly with time, one needs to be careful. The other thing is the highest pressure drop, when do you expect that you are going to get? When the fluid is at the highest temperature and the lowest pressure. Under what condition this happens? This happens generally during the desorption or the regeneration step. We get the highest temperature during the TSA, the desorption step of the TSA cycle, and the lowest pressure during the desorption step of the PSA cycle. So, therefore, when you are finding out pressure drop, it is important that you find out the pressure drop both for the adsorption as well as for the desorption process. Often we find that the pressure drop, it is high for low pressure gas phase applications, right. For such cases, one can opt for a shallow adsorption column, right, which means that one can go for a low L by D ratio, the diameter is larger, the length is smaller. Under this case, the lower pressure drop can result, but be very careful, because moment you go for a low L by D, it results in maldistribution. Therefore, in order to ensure uniform distribution, we might have to use manifolds, baffles, screens, etc., which again increases the pressure drop. And definitely we need to keep in mind that there are certain special shape of the adsorbent particles which are being increasingly used now in industries, particularly to keep the pressure drop low in low pressure gas phase applications. These typical shapes are say monolith particles, trilobe particles, etc., which can be adopted in order to ensure a low pressure drop. Well, so with all these things, now I think we are in a position to just look into a typical problem of adsorber bed design. We start with the gas phase adsorption. What do we have? What is our feed? Our feed is an air stream. The flow rate of the air stream is provided, the feed condition is provided. If you recall, in the beginning of the class I had said that normally we have the feed condition, the feed flow rate, we also have the adsorbent concentration in the feed, and we are also specified what can be the maximum adsorbent concentration in the effluent. Based on this, we have to proceed. If you recall, in the last class, what did we say? The first step will be selection of adsorbent. Now, when you select adsorbent, definitely we have to keep in mind that which adsorbent is conventionally used for such a system. Along with that, if by some chance if you have some particular adsorbent for which the breakthrough curve or the breakthrough data are available, it is going to be additionally useful for you. So, therefore, considering these things, what we did, we selected a commercial zeolite adsorbent silicate, and from the literature data, the reference is there which you can refer for further references. In this particular paper, we found that they have provided experimental data on column adsorption for acetone removal from air. So, fortunately, we take up the properties of the adsorbent that they have provided, and we also take up the breakthrough curve that they have given us, right. So, therefore, with this particular breakthrough curve and with the adsorption column details that they have provided, the adsorbent details that we have provided, we proceed with the design of the adsorber for the feed concentration which has been provided under the conditions which are given here. So, to start with, what do we do? To start with, the first thing that we do is that using this particular breakthrough curve, what are the things, the breakthrough curve we have provided? Here we know Ci, this is equal to 0.013. C breakthrough, if you see, I have marked all of these, this is 0.004. So, therefore, from here I can find out what is CB by CI. I will just write down the values, you can check it up for yourself. We assume that we can operate the bed till CEX by CI about 0.97, we can operate it. So, therefore, this gives you the CEX value, this is the CEX value, this is the C break point value, this is the TB, this is the T exhaustion, right. So, therefore, from here we get CEX equals to 0.1261. TB, we know TB, this is equal to, if you see it carefully, it is 28.3 minutes. T exhaustion, this is 81.5 minutes. So, naturally, from there we are in a position to find out F. F is what? Just like I had told you, this particular area divided by the total area. So, therefore, in this particular case it is naturally equal to 26, So, for this particular case, more or less this is equal to, if you find out this particular shaded area from t equals to 0 to t equals to 28.3 divided by the area from t equals to 0 to t equals to 81.5, more or less you are going to get F equals to, you can check it out, F equals to 0.67, which is slightly less definitely, right, but we are going to proceed with this. Now, from here then from here what do we get? Suppose we would, once we have known F, we can find out the adsorbate transfer in the pilot plant. Pilot plant I will be per unit volume, per unit bed volume, right. So, therefore, for do I get this? This is naturally equal to Q pilot CI minus CB divided by V pilot. This, if you do, you can check it up. The Q pilot was 2. The change in concentration, I have already written it down. So, you can check it for yourself. The volume of the pilot plant, if you remember, it was given. So, from there we find out this is 0.252 moles per hour liter of bed, right. In the same particular way, we know that 67 of the bed it gets utilized. So, here the data of the pilot plant, they are already provided. We know that the 67% F equals to 0.67. So, therefore, we can also find out the total amount of adsorbate transfer rate per unit bed volume utilized in pilot plant. You can definitely find this out. This is nothing but equal to the thing which you had found it out, which gives you to be 0.376 moles per hour liter of bed volume, right. So, from that you know that what is the adsorbate transfer rate in the plant. The Q of the plant, it is provided to you. So, from here it is nothing but the Q plant CI minus CB, you can find this out, and then you can also find out the adsorbate transfer rate per unit volume of the bed utilized. So, adsorbate transfer rate per unit bed volume utilized, this also you can find this out. So, therefore, from all these things, more or less the adsorbate loading could be found out. Now, suppose we assume a T cycle. Normally, for such operations it is 8 hours. from where we can find out that the adsorption part usually it can be assumed to be 4 hours, right. So, therefore, during this particular 4 hours, how much amount of adsorbate transfer has happened per hour we know. So, therefore, the adsorbate transfer in the plant for one cycle, that you can very well find it out, right. More or less from there you can, sorry, there was a mistake, I think this one was not point, no, this all right, fine. So, the adsorbate transfer rate in the plant you can find out. The adsorbate transfer rate, it is roughly equals to 18.9 moles per hour, and so from there we can find out what was the adsorbate transfer rate in the plant. Definitely that can be find out. This is 4 hours into so much amount of moles, right, which gives you around 75.6 moles. So, therefore, the bed volume that gets utilized, that is how much is that going to be? That is going to be 75.6 by the adsorbate loading per unit of bed volume, which was equal to 0.1773 moles per liter of bed. So, therefore, from there we can find out the adsorbate transfer in the plant, and from there we can find out the bed volume that gets utilized, right. Now, once we can find out the bed volume that gets utilized, we can find out the actual bed volume. So, this is the utilized bed volume, we can find out the actual bed volume. How do we find the actual bed volume? We consider this, and then we also take a safety factor of 1.3. So, using all those things, we can find out the adsorbent volume in the plant for operation up to the breakthrough point, right. So, from this, if we can find out the adsorbent volume which is necessary till breakthrough, we can find this out, and once we can find this out, we can also find out total adsorbent volume to be provided. What will that be? That is going to be, suppose the adsorbent volume till breakthrough, it is near about equals to say 554.3 liters, just check up these particular quantitative measures. So, then in that case, this is going to be this value divided by F into 1.3, and from there you are going to get the total adsorbent volume, which will be coming to as 827.335 liters. Once you know the total adsorbent volume that has to be provided, you can definitely find out the mass of adsorbent that is required. This is just the volume into the bulk density, and as I had already mentioned, I think the bulk density was equal to, there is a small mistake here, this bulk density, this is equal to 700, this has got interchanged. So, therefore, from there we can find out the total mass of adsorbent that will be required, and finally, if you do it, you are going to find that the total adsorbent mass required will be something of this sort, right. So, therefore, what we did, we used the breakthrough curve, we found out the F. Once we found out the F, then we tried to find out what was the adsorbate transfer rate in the pilot plant and for per unit volume of bed utilized, and then we found out what is the actual adsorbate transfer rate in the plant per liter of bed utilized, right. And so, from there we know that how long this particular adsorption process will occur. From there we found out the total adsorbent volume that has to be required in the plant, and also the total amount of the total mass of adsorbent that will be required. Once this is done, next thing we would like to find out or finalize the dimensions. Now, normally for finding out the dimensions, since we will be operating with a vertical column, so definitely for a vertical column, you will be learning more about this when we go for discussions on pressure vessels, etc. Generally, this lies between say 3 to 4 or 3 to 5. So, accordingly, we assume that for the actual contactor, L plant by L by D of the plant, we have assumed this to be 3. You can also assume it for 4. So, from there what do we get? We get pi by 4 D square into the L plant, where this L plant is nothing but 3 D. So, from there we know the entire volume of the adsorbent volume, we know what is the total volume that is required. So, from there using this particular equation, we can find out the D plant and we can find out the L plant. For our particular case, what we have obtained is D plant, it is nearly equals to 0.7 meters, L plant it is near about equals to 2.1165 meters. So, therefore, we find that more or less for gas services, the diameter of the plant it lies between 0.3 to 1.2 meters for gas services, and we find that in fact just to accommodate this, we had done this calculation, and now we find that this is fine, right. Once we have found this out, now we need some checks. If you remember, what are the checks? What is US plant, you need to find out. Under this condition, more or less we have found out that the US plant is 0.11 meters per second. What was the US pilot that we had found out? That was 0.29 meters per second. So, what do we find? That in the plant the velocity is lower. If the velocity is lower, there is no problem, we are going to get sufficient contact between them, and it also provides a sufficient residence time. So, definitely we can go ahead with this particular situation. We also need to check L by dP and D by dP. This is the pellet diameter. If you can check, you will find that both of this is also greater than 100, this is also greater than 20 to 30. So, these things are also fine. So, we have checked the superficial velocity, we find we can go ahead. We have checked that channeling, mixing, everything is ensured. Next, we need to check the EBCT. The EBCT in this particular case, we find that this is nothing but the V plant by the Q plant. So, this we find it is more or less say 19.856 seconds. Now, we find that this particular EBCT, the EBCT for the plant, this is greater, much greater than the EBCT for the pilot scale. For the pilot scale, the EBCT was 1.8 seconds. And we find that it is not only greater, if you remember, we had said that more or less EBCT should vary between, there was some particular limit, and so we find that more or less it is less than 30 seconds, which is the permissible limit. So, therefore, the EBCT is also greater than the EBCT that we had obtained from the pilot plant data, but since this ensures a better contact, and so therefore, we go ahead with this, right. And after that we try to evaluate the pressure drop. If you try to evaluate the pressure drop, you will find that more or less all the data are given. You can find it out, and I had calculated it, that also falls within the permissible limits that were there. The bed pressure drop was much small compared to the total pressure of 1 atmosphere, and therefore, we find that this is fine, we can go ahead with this. After it was completed, then more or less the design summary has been put up in this particular form, where the total amount of adsorbent, the length and diameter, etc., all those things are there. the only thing which is remaining is the design of nozzles etc., which we will be taking up when we go for the discussion on the pressure vessels. So, this was a typical problem for gas adsorption. In the same way, I'll just touch upon another adsorption problem for wastewater treatment. Again, in this particular case, the total Q is provided, the initial concentration is provided, the permissible concentration is provided. Since this is wastewater treatment, if you recall that activated carbon was a potential source. So, we select activated carbon, and from the table that I had shown you, I go for a coal based activated carbon from where I select this particular bulk density, right. And in this particular case, we found that the data which are available, they are in terms of cumulative volume. We do not have a breakthrough curve, but we have a cumulative volume in this particular case, right. So, therefore, here I have listed down all the different data which are available for the pilot plant, and also the flow rate etc., the particle dimensions, everything has been put down here. From there, first what I do, I find out the LR plant, right. LR plant, what is the LR plant? This is equals to the LR pilot. What is the LR pilot? It is Q pilot by the cross sectional area of the pilot plant. We find that more or less if you calculate it, it is going to be 141.08 LPM per meter square. If you recall the limits that I had placed, the limit was between 80 to 240. So, therefore, this limit is fine. Now, we would like to keep this LR for our case. So, if we want to keep this LR, from there we can find out the A plant. From the A plant, we can find out the D plant, right. We know the Q plant, we know the LR plant. So, therefore, we can find out the D plant. In this particular case, we found that the D plant, we had obtained it as say 0.97 meters, which we will be taking it as 1 meters. After that, what we do? We go to find the EBCT pilot, and we take it as same as the EBCT plant. What is the EBCT pilot? It is V by Q for the pilot plant, and this we obtain as 12.404 minutes. Taking this particular EBCT, we find that the L, we can find out the L plant in this particular case as well. We find that the EBCT that we get, that is also within the permissible limits of 6 to 20 minutes. So, therefore, from there we find out the L plant. L plant is actually 1.6 meters. Now, this is slightly less. As I had said, for vertical columns we would like to have 1 to 2 meters, right. So, sorry, the L plant by D plant should be between 3 to 5. Anyhow, let us proceed, and then we might change. From there we find out the V plant, and then we would like to find out the fraction utilized of the adsorbent bed. So, for that we would need to have the data which I have already shown you. If we assume that the curve was more or less symmetric, then in that case we can find out the F from the adsorbate transfer from T equals to 0 to T equals to TB divided by adsorbate transfer from T equals to 0 to T equals to T exhaustion, right. From there, if we find it out, you will find that it is nearly equal to 0.93. This adsorbate transfer, this is nothing but VB into CB minus CI divided by VB into CB minus CI plus V exhaust minus VB. We assume that the average concentration is the arithmetic mean. From there you can find it out. This is actually quite high. So, therefore, For the actual plant, what we do, we assume the F to be equal to 0.85 and we proceed, because naturally when the adsorbent bed it starts operating, and also due to other uncertainties, little amount of maldistribution in the larger bed, the F utilized will naturally be much less. And after that we also find out the adsorbent loading in the pilot plant. We also find out the adsorbent loading in the actual plant. We assume that the adsorption in the time of adsorption is equal to 4 days, and in this particular way we proceed. Once we have found this out, we can find out the total bed volume. We can consider F equals to 0.85, take up a safety factor, and then finally we can find out the bed volume. When we find out the bed volume in this way, we find that it is slightly higher than the bed volumes which we had found out from the pilot plant data. Anyhow, we proceed with this, and in this, from this bed volume, considering L plant equals to 3 times the D plant, we recalculate the length and the diameter of the column and finally arrive at the dimensions. Once we have arrived at the dimensions, it was important to check the loading rate in this particular case. We found that the loading rate in this particular case, it was around say 104.167 liters per minute. No, sorry, not 104, it was 183.57 liters per minute per meter square, which is again within the permissible limits. So, we proceed with this, find out the mass of the adsorbent that is required, and we also check up the superficial velocity in the plant. After every design, we need to check up LR, the US plant, these things we need to check up, and then we go ahead with the pressure drop calculations. So, once if you proceed with these particular calculations, and these checks also I have written down for your convenience. So, once you have done, more or less the design output is as shown in this particular case. You can proceed for yourself. In case you have any doubts regarding the illustration problems, we will be happy to address those doubts, and with this I conclude my discussions on adsorber design. So, thank you very much for today.